All right, we have some great high quality clip art to start us off here. This is cool. When I was a kid, all computer images looked like that. So it gives me a lot of good nostalgic vibes. You guys maybe think, wow, that's pretty lazy clip art there, boss. That's okay too. But today we're talking about analog to digital conversion and digital to analog conversion. This may be a function you've either used already, which you have briefly in some other classes like your 179, maybe some others. But today we're going to talk about specifically zoom into the digital infrastructure that makes these conversions possible, and how we can use the tools and topics we've generated already in this class. So the idea of counters and flip-flops, to both store AC or analog numbers coming in, digital numbers going out, how we're going to convert those back out to analog quantities. And so we'll have some details of the inner workings of that. The electronics we're going to talk about today are equivalent to what is on like your Arduino Mega board, for example. We have those analog pins that can do certain levels of generation using some conversion algorithm electronics that we're going to talk about today. Okay, I'll move on from this slide. I know that picture is burning your eyes. Here we go. Grab my clicker so I don't have to be tied to the keyboard over here. Digital to analog representations. You've seen slides or this concept a number of times, but basically when we have an analog quantity continuously moving up to the resolution of nature, we get nice smooth curves over time if you're measuring a voltage over time, for example. When we need to move this to a digital realm, through a process known as sampling, and that key word is its own entire discipline within electronics, the idea of sampling. But if we have a signal over time we want to make digital, we sample it at known time increments. And when we sample the value into a known variable size, a known number of bits. And that's what's going to give us the resolution of how accurately we can capture that data. So if you're maybe sampling to do a hobbyist Arduino project, an 8 or 10-bit sample may be sufficient. If you are creating audio in the studio to make your new recording of your music and you want very high quality, you might have much larger bit sizes of your samples, because the more bits of sampling you do, the more accurately you retain that original value. So we have a bits per sample, and then we also have how quickly are we sampling, right? So if you sample only once at the beginning of this waveform and once at the end, it's essentially impossible to reconstruct the contours of that analog waveform if you're not sampling quick enough. So if you look at, find an MP3 file and look up the standard online, you'll see that there's both a bit size per sample and a speed at which it is sampled. So you need a number of samples quickly and then of a certain accuracy in order to reconstruct your analog signals back out from the digital world. So we're looking to capture analog in to binary, essentially, so we can process it with our algorithms and then output it back to the analog world. So if you play music out of a speaker, you're converting back to analog, because we are all analog creatures, and sound moves through the air in analog fashion, all that kind of stuff. What it can look like to us, and where we're going to extrapolate this idea further, will probably be in the form of a block diagram. So we'll have some signal coming in, we'll have some digital data coming out. All the details, if you looked up a manufacturer data sheet for an A to D converter chip, would detail the specifics of how quickly does it sample, how many bits are used, what options do you have, things like that. So this is the higher level representation. Just a note about bit sizes, and this is maybe a bit of review from other things you've gleaned from other classes, but the number of bits gives you the number of analog levels you can record. And so you know, with a 4-bit system, you only have so many levels. With 4 bits, you only have 0 to 15, so 16 different levels to record out of this gradient of analog values. And so if you've ever seen like the step-shaped digital output, that's going to come from this. And we'll look at that in more details in a little bit. Most A to D and D to A circuits use op amps. They have some good, very high input impedances, so you can not require a massive power usage to do your conversion. You get high voltage gains, low output impedance. This is a very basic op amp circuit, just using for gain purposes. And we're going to use a similar circuit when we move forward. But you all remember from your classes on op amps, which some of you may be in right now. Have you heard of op amps?
We've already.
You know about op amps? Okay, you guys know about op amps. All right, so you know that op amps have these plus minus terminals with that virtual ground. So it looks like ground, but it has infinite impedance. So you have no current flowing in there. And you can set up a circuit to allow some sort of current to go here. That current's going to want to flow, and then we have a gain feedback resistor going on to make this. What is this configuration called? Anyone know it offhand? Feedback?
Is it
Feedback or inverted amplifier? Is that right?
it is inverted.
Yeah.
It's one of
So we have that amplification circuit. Let's talk about this. This is that same circuit, but we have two possible, or well, two included parallel tracks going at the op amp being added to that feedback circuit. So this is your feedback resistor up here, feeding back from V out. And these are input side resistances. So the first thing we need to know when looking at this circuit is what are the currents on those two legs, the 10K leg and the 5K leg. So who's got their calculator on hand that can tell us? We have 12 volts over 10K. Who can do that Ohm's law for me for what's the current?
1.2 milliamp.
0.2 milliamp for that first leg. You can do
1.2.
and erase your scribbles here. Shouldn't call them scribbles. Your artwork that you worked very hard on.
That's dedication right there.
That's dedication right there. Yeah.
Yeah, he never solved it. Let's try this.
All right. So we have 0.2 milliamps going here.
1.2.
1.2, yeah. Yeah, so we're doing 12 divided by 10K. All right, and how about on this leg? We've got 10 volts over a 5K ohm. What's our current here? 10 divided by 5K.
2 milliamp.
Well, 10 divided by 5 is 2. Yeah. Okay, so 2 milliamp, 1.2 milliamp. So we've got those currents flowing into our op amp. We know from what we just said, current's not going to go into that op amp, that virtual ground situation. So it goes out and over our feedback resistor, which is off my screen here a bit, but what is that? 2K? Yeah, 2K up there. So we now have these two currents flowing into this node and a total current of 3.2 milliamp going over this 2K resistor here. So your V out is just that 3.2 milliamps times the 2K resistor. Your milli and your K are going to cancel out, right? So, 6.4 volts at the output. Because of how it is referenced, it's going to look like minus 6.4, right? For the inverted amplifier style. What we are looking to get out of this is that with this type of setup, we can just add together the current contribution of a bunch of parallel legs. And the current contribution changes based on how we weight these resistors. So if we use the same voltage levels, but we, change the resistor weights, we can get currents that are proportional to each other in very known fixed ways. But I don't have it here. This is a slightly more complex, but not by much, version of that very same circuit where we have a 5-volt source. We have a bunch of digital switches, which would be something like a transistor that we turn on and off. Could also be a physical switch, potentially. Then we have resistors that are related to each other by a factor of 2. So here's a 10K, 50K, 100K, 50K, 25K, and 12.5. So divided in half each time. When your resistance is getting lower, our current is doing what?
Getting higher.
Getting higher, exactly. So over on this end, our lowest resistance, we have the highest current contribution. And we can see the labeling D3. Because they're all a factor of 2 related to each other, these can represent your 4 bits being activated. So for a 4-bit system, this ladder circuit here, binary weighted resistors, can be used to create an analog output with only 4-bit resolution, but the current contributions will be all proportional to each other the way our bits are by that factor of 2. And those currents will be added together, sent over a feedback resistor, and then we get some analog output. And we can see here, for our various digital inputs, like for example, 0001, we would get a 1-volt out. So 000, so no current coming from those, and a 1 gives us a 1-volt out based on just the Ohm's law over that resistor. And that trend continues, and these are negative, by the way, but the negative's left off. But with this circuit, putting in these digital values gives you 16 different levels, 0 volts through 15 volts. So this is not a decimal equivalency, this is an actual voltage output that happens from that circuit. And so this circuit converts with 4-bit accuracy a digital number in binary to an analog output. And if we plot that analog output, it's going to look like a step functions because it's a 0. When you flip your digital to 1, it goes to 1. So there's no smooth transition, but it creates 16 different steps that can be represented by this circuitry. So this is a very rough way, direct way though, of doing digital to analog conversion with this type of circuit. And that's what would be contained in, this would be the just system level view of that. So the binary weighted digital and analog converters do have some drawbacks. We need different resistors for each leg. And so we're designing potentially a high level fabrication, advanced manufacturing process for a lot of different resistances. And so doing that accurately can be challenging. And with a lot more bits, it's not really practical to expand out and design more and more different sizes of resistors. So another method of doing this is to use an R over 2R ladder. And the advantage here, the setup is the same, but the advantage is you're only designing one kind of resistor, resistance R. And the weight of each leg will be as shown here. So we have 2R, which is just 2 of this resistor, in series. But if you do the math here, and we work our way out, so here we have 2R and 2R in parallel with each other. And so 2R and 2R in parallel with each other would be what equivalent resistance?
R.
It would just be R, yeah. So that has an equivalent resistance of R. And so if we have R plus the equivalent resistance of R, this whole chunk is 2R. And we have, again, 2R and 2R and R. You can kind of work your way backwards and find that the equivalent amount of resistance actually is the same factor of 2. So here's a 2R, and you work all this out, and your resistance gets higher and higher by a factor of 2 with this setup. And I'm not walking through specifically the parallel calculations the whole way back, but your bit layout's the same. The advantage is purely in the manufacturing. If you have a really good R resistor, you can create all these bits with that same resistor copy pasted in your fabrication process. And then your output has a 2R as well for your feedback resistance. And some calculations added on top of it here. If you get to this node, you have a 2R resistance here. Remember, there's the equivalent resistance when you work your way back is also 2R this way. So your current goes half of it there, half of it there. All of this has an equivalent resistance of 2R again. So half of your current goes down, half goes there. You're splitting your current in half each time. So you get that same binary weighted attribute. And again, those current contributions are summed by the summing amplifier set up here over your summing resistor and gives you a V out, which will be an analog quantity, you know, a digitized analog quantity or at specific steps, but at your V out. Here's that stepwise function and what it would look like. So if you are counting up with a 4-bit counter, going through an A to D converter and reading that output, this is what it would look like. Again, classic example of an analog line would be a straight linear line there, but in the digitized version, you know, we have that shape. Or quantized is the word you would use in sampling. We tried, yes. And the more bits you have here, the smaller those steps can be. So if you're trying to record yourself playing the guitar and you want to very, very accurately recreate that, you might need a lot more bits. So 64, 128, those are common levels, and even higher is used for high quality audio sampling, for example. So all of this functionality, of course, is integrated at chip level. And you can find all of the functions we just talked about on sort of a data sheet level of a chip. Here you have let's see, so this has an 8-bit D to A converter being shown here. We have all our incoming A bits and then an output somewhere on here, I out, right here. So notice, out of this we get an I out, so you can include your own op amp and feedback resistor. This just is the resistor network. They're the R over 2R ladder all combined together. Then you can choose your own feedback to set the voltage level that you want coming out of that type of chip. So usually you have the option of adjusting your feedback, you know, resistor so that the voltage level is whatever you want. Or whatever you need for your specific application. And you can recreate this, you know, with chips and then watch those steps happen on an oscilloscope. If you put a counter, like an 8-bit counter behind those input bits. This may be what we do for our lab on Thursday in multisim, but I still need to work out or look at the details. This is a very fun one to do on physical chips as well, which is how it was being done back when I was in school, because you get to actually view that on a real oscilloscope. So we'll maybe try to make it a little bit fun, but it'll probably be multi-sim based. Okay, a lot of issues can happen within these electronics doing conversions. Here's a couple different errors that can occur, or types of errors. Here's a non-linearity, meaning your step sizes are not uniform as you go up. Here's a higher or low gain. So you may be trying to fit that dotted line in the middle. If your gain is too high, you'll be too steep. If your gain is too low, you're kind of drooping below the ideal line. And here's a missing code where there wasn't a difference seen between that. That would be difficult to achieve with hardware. But if you're using maybe a software lookup table of some sort, you know, perhaps you could run into that type of issue. Here's a non-monotonic order. The most frequent reason you will see this is because your inputs are not wired up from least significant bit to most significant bit. Maybe you swapped one or the other. That count is highly irregular now, but it's because some significance of bits have been changed. And you might see something like that. And here's an offset error where you may just have a DC bias kind of pushing your analog values over. And so everything's just as a base offset higher than what you'd want or lower than what you want. That would be an offset error. Relative accuracy is really, there's a lot more to that in the discipline of sampling under electrical engineering technology. But how accurate is your system to the actual analog waveform you're trying to capture or recreate? And then there's a settling time. So if you have a very high speed application and you change your digital inputs to be converted to output analog, how quickly does it reach that next level could be an issue. And there may be sort of this overshoot sampling that looks like a control system. There could be a different shape of ramp up. It's kind of based on the electronics, but it's basically how quickly does your converter respond. On our Arduino Megas, for example, you'll look in your 279 course specifically at our analog conversion hardware and how quickly it can act and create outputs. And all that's captured in the data sheet for the Atmel processor. So more on that a little bit later on in a different course. And here's just an ideal input to output 3-bit ADC without any of the errors we just discussed shown. You can see that here. Since it is input to output, we've reversed direction now. We're taking analog into digital out. But we have input to output, so that is again a transfer function similar to what we looked at with our inverters discussion in the Schmidt inverter earlier on. So there are some other A to D conversion technologies. The ones we've talked about so far are some of the more rudimentary or accessible. You could breadboard those things. But we're going to build up a little more to see more what the current state, if you just buy a microcontroller off the shelf, what that might look like. One other honorable mention, though, is the idea of parallel encoded A to D. This is done purely with op amps being used for comparisons. So you have some analog in, and it's just compared against 7 volt, 6 volt, 5 volt, 4 volt, 3 volt, 2 volt, 1 volt. And you'll have a direct kind of encoding of what that analog value is. This is a very fast mechanism because it's all done in parallel immediately, but you can see how if you expand it to lots more bits of information that you want, which would be much more analog levels to detect, many more steps in that conversion, this circuitry blows up very large very quickly, so it's not ideal. And so moving towards a more modern state of conversion takes advantage of our high-speed counting available in our systems. We have high clock rates, things like that. So first, let's look at a counter ramp A to D converter. And so what happens in a counter ramp A to D converter? We have some analog in that we're trying, this is the value we want to capture. We're moving analog to digital. It is comparing it against a D to A conversion here that starts at 0. So initially, the analog output here is a V out of 0, and it compares those. If the analog coming in that you want to capture is still greater than that, it increments a counter, an 8-bit counter in this case, up by 1. So you move up one step of that step diagram, create that analog output value, and then compare it. If it's still larger, you increment your counter up by 1 again, so you move up one additional step on that diagram, create the analog output, compare it, and you continue that process until you reach a point where your analog created from this counter and then converted is greater than this. And then you stop. You say, okay, we've now exceeded the input voltage. We're going to back it up by 1 and call that our analog value that we are reading in and store that binary to your output. So once you have, so basically you're below your VN, analog VN, you just count from 0 up until you reach it. Once you reach it, you stop counting, and that's your digital equivalent that you're going to store in a chunk of memory over here, just 8D flip-flops, as it's shown here. This type of system can only run as fast as your oscillator can run, but it's limited by how fast your conversion happens. So if this has, you know, if that's a 16 megahertz clock, but this only runs at 1 hertz maximum, you're limited by how fast you can count up and then convert for that comparison to occur. So this is a more efficient hardware size, footprint wise, way of creating a piece of conversion circuitry. But it's not the fastest we can do because we do start at 0. So if your analog is near the top, you've now got to count and compare, you know, all the way up to near maximum if you're near the maximum input range. And so the timing that this could take is variable. In digital systems, we do not like variable timing. We like to know very precisely the time that something's going to use. And so the approach we're going to end with today is the idea of successive approximation, A to D, used in most modern AD ICs, and similar to the counter ramp we just discussed. However, the way that it narrows in on the input analog is slightly different. It'll work as we're going to talk about here. So instead of starting at 0, you start in the middle. So if you have a 10-volt range, start with 5 volts. Compare it to the output, say, are we higher or are we lower? Now, to set 5 volts, that's only our most significant bit, right? If you think 256 for an 8 bits, the most significant is your 128. So that first bit controls half of the weight of the number. So we just turn on the first bit, leave all the others off. Convert that. Say, is that analog higher or lower than halfway in the middle of the range? And then turn that first bit, either leave it on if it is higher or turn it off if it is lower. Then we check the second bit, which will, so if we divided, say we have a 10-volt range, and the first bit, blanked out my screen. The first bit divides the 10-volt halfway. So here's 10 to 0. The first bit said 5 volt. We said higher or lower. The second bit would then divide either the top half or the bottom half in higher or lower. So it's kind of like a, I don't know, like a Price is Right guessing game or something. We say higher or lower. Okay, then check the next bit. If we're up here, is it higher or lower than this half? Or the lower part, is it higher or lower? Then we leave that next bit, D6, on or off. Then we can divide up the third range. Is it higher or lower? Then we can divide up that range, higher or lower, by moving over 1 bit at a time. And the advantage of this algorithm to do this is it only takes 8 checks. No matter what your input is, the timing to get to the end is always the same. And so there are some cases where this could be a little slower than starting at 0 if your analog VN is very low. But in general, you save a lot of time using the 8 checks method rather than doing a sequential count from 0 and going. And this is overall schematic of this. I'm not going to hand wave go through every step of this, but here's an example that you can walk through kind of offline with a sample VN. But what we see in general, though, is that it checks the first bit for higher or lower. Then it checks the second bit for higher or lower. It checks the third bit, the fourth bit. And if the value is still higher, the bit stays on, like this first case. If the value, if it turns it on and it's lower, it turns the bit back off and then moves to the next one. So it takes 8 checks before we get to the end, and then your entire binary is just stored has those 8 bits. And if you're looking at the V output that you're checking against, so if we're looking at 6.85, it's higher than 5, but then it's less than 7.5, so we turn that bit back off. 6.25 is the next half increment. It's higher than that, it's higher than that. And you can kind of follow through this example, looking at the 2 slides side by side offline, be a great way to just wrap your head around this. And so this is what you would find, this is what you would find in an integrated circuit that you activated on an Arduino, for example. You have your hardware circuitry. It happens to be connected to one of 16 different pins, your A0 through A15 on the mega board, for example. But you only have one piece of this hardware, and so those pins are multiplexed to take turns using this hardware. So this takes 10 milliseconds to run, and you have 3 pins trying to do conversions at once. You can work out the timing on how they share that pin, or how they share that piece of hardware. But here you can say conversion speeds up to 17 microseconds. So we're not on milliseconds, we're smaller, but microseconds is still a little slow compared to a 16 megahertz clock. So there are considerations to make. You can't change it or call those values too quickly. And that also limits your sampling speed. So we talked about the rate at which you take samples. Those are limited by how quickly you can create conversion. How quickly you create conversions is based out of how long does this process take to run. So you can see just another form of that setup shown here. And this is just the data sheet or chip form view, but it's the same circuit we were just discussing in this situation. Okay, so any analog quantity can be represented in a binary number, but the number of bits determines how accurate that sample will be. A higher resolution gives you a more accurate representation, as you might expect. There's also the sampling speed that comes into consideration when you're trying to recreate an analog signal from recorded data values. So there's the reading in, sampling, and then also to recreate a structure, you need to take so many samples. In the realm of sampling, balancing these things are key. So that's the end of our lecture for today, just the A to D and D to A conversions.